for being one of the authors of this, the work I'm going to talk about. So yeah, huge thank you to all the organisers. I know there's been a lot of work going on behind the scenes. A lot of people haven't seen, kind of, I've seen some glimpses of it kind of behind that, but you know, it's just fantastic to be here, kind of. Yeah, really, really interesting talks. And it's really good to be here celebrating Alex's birthday as well, kind of. So I'm going to just go on to my next slide, which is probably better than the first one. Okay, so this is probably what I should have had as my opening slide. So very thank you to Vaso again for producing pictures of this is all the people, the work involved. So Philip, myself, Vaso, yeah, who I think is the same picture, yeah, and Anna Miriam Benini. And so it's been work that's sort of developed over the last several years. Kind of, we've now got 3 papers leading up to the 4th paper. And the title that Vaso has here is much nicer than the title. So let's go with this title, which is simply Collective One Domains and Beyond, kind of in Dutch. So that's a kind of better title for what I'm talking about, really. Okay, so it's been a lot of fun. A really, really nice group of people to work with. It kept us going through COVID. We kind of had lots of Teams meetings and things, kind of. And before that, you know, trips to Barcelona and things, and so yeah, a lot of fun. Okay, so the title of the talk is about what happens when you compose inner functions and you look at non-autonomous dynamics, but the motivation for the work that I've talked about comes from complex dynamics, which is like kind of today, and where Alex has been hugely influential. So we're going to start off kind of talking about the background and some of the initial results which we had, which were in complex dynamics, and then the sort of second part of the talk move on to where that's taken us, kind of sort of broadening out from beyond that to the results that you can prove. So obviously follows from Walter's talk we had at the beginning. So we're looking at iterating an analytic function of the complex plane. The particular setting we're interested in is iterating entire functions. So again, this was mentioned in Walter's talk, but the Fatou set is that if you take a point and you iterate it, and then the Fatou set is if you take nearby points, then they have similar behavior and iteration. So Walter talked about normal families, it's equicontinuous, but points that start nearby, they stay nearby to each other as you keep on applying your function repeatedly. So it's a stable set. And it's actually this set that I'm particularly interested in for this talk. So the opponent's completely invariant. And then the complement of those points is the Julia set, or the chaotic set. So you can have points arbitrarily close by that can have very, very different behavior and iteration when you keep on applying your function. Okay, and Walter's talk was about the escaping set, and the escaping points can be either in the Julia set or in the Fatou set if you're looking at entire functions. So for polynomials, the escaping set's all in the Fatou set. But for entire functions, they'll be in either of these sets, depending on what class your functions are in. So for some classes, that's not the case, but in general, it is. Okay, so these are the basic sets we're looking at, and I'm particularly interested in the Fatou set, the kind of the points where the set of points which stay close to each other under iteration. Okay, so what we're going to look at is components of the Fatou set. So you have this set of points and you split it into its connected components, and then you can do the same thing. So initially we said, okay, you take a point in the complex plane, you can ask what does that point, the orbit of that point, as you keep on applying your function. If you take a component to the Fatou set, you can ask the same thing, what happens to that component of the Fatou set if we apply our function to it. So we're going to let UN denote the Fatou component containing the iterative U. Okay, so hand-drawn picture. So you have your Fatou component U, you map it under F. It'll always map it into another Fatou component. It maps onto another Fatou component, but there could be a point that's emitted when you map, kind of, if you've got exceptional point. But you can just think of this orbit of Fatou components that we have here. And then you can ask, okay, what's happening with this orbit? So first case which you might have is that you periodic cycle of Fatou components. So you map forward, and then after a finite number of iterates, you come back to the Fatou component you started off with, or maybe the Fatou component maps into itself. This invariant. So that's the sort of simplest case that might happen. or it could be pre-periodic. So you might map forward a few cases and then you map into some cycles. And then after that, you just keep on going round this cycle of Fatu components. And then the third possibility, which sort of was mentioned in Walter's talk, that you could have a wandering domain. So a wandering domain is that you never go into a cycle. So each time you map forward your function, your component maps to a different Fatu component. But every time you keep on applying it, you keep on mapping into a different Fatu component every time. And that's what I want to talk about kind of for the first part of the talk, this case of wandering domains. So the periodic Fatu components are really well understood. So this all goes back to the sort of the application sort of essentially back to Fatu and Kramer, sort of right at the beginning of people when people are looking at complex dynamics. And there's sort of certain number of types, and there's very precise descriptions of what's happening inside these. So you have a attracting components, parabolic components, see all this, that kind of thing, and there's very precise description of the dynamics inside those. So the periodic Fatu components are really, really well understood. And that leaves us questions about, okay, well, if you have wandering domains, what can we say about the dynamics in those? Because we know really well what happens in the periodic ones. Okay, so the first question would be, well, can these wandering domains exist? Because if we know what happens in periodic ones, those are really, really nice. So if we don't have any wandering domains, then life is suddenly a lot easier. Okay, so big result due to Sullivan in the 80s that if you have a rational function, then there are no wandering domains. So it's a really, really big result. Kind of. And so for rational functions, that means you know everything about your Fatu components. It has to belong in one of these classes of periodic Fatu components where the dynamics are really, really well described and you know exactly what's going on. This is the Fatu set is really nice in this case. There's only these sort of 5 different types of behavior that can happen, well described. Okay, but what about entire functions, which is what I want to talk about. Okay, so the first examples of wandering domains actually came before this big result of Sullivan, kind of. So this was my supervisor, Noel Baker. So there was this sort of quiet period kind of between there was Fatu and Julian, in sort of the sort of start of the last century. And then kind of when these sort of like results of Sullivan and pictures and things with the Mandelbrot set and things, kind of everything sort of, exploded a lot, and it kind of becomes very popular in the 1980s, which was sort of when I did my PhD. But before that, Noel Baker, who was my supervisor, who was a very quiet, modest man, was sort of proving lots of really, really interesting results that people weren't actually paying that much attention to at the time. And there was activity going on, but it wasn't kind of so much noticed. And this is actually a really big result to kind of show that there really is wandering domains. But I think at the time it was kind of, and he was not the kind of man to stand up and go, wow, I've proved this fantastic result. It's really, really interesting. He just go, well, are these wandering domains? And it was really also the results actually came in sort of 2 papers 10 years apart. So the sort of 10 years before this, he proved the first part of it, where he basically he had an infinite product, and he constructed by choosing the terms in the infinite product carefully, he was able to show that you can get an annulus that maps into a bigger annulus, that maps into a bigger annulus, that maps to a bigger annulus, so on. So he sort of set up what could be a wandering domain. It was an annulus that mapped to a bigger one, that mapped out to a bigger one, and that out to a bigger one. But what he couldn't show at that point was it was possible that these annuli were all joined up by the bits of the Fatu set in between. And that couldn't happen with another 10 years. So we had the basic idea of how you could get a wandering domain sort of 10 years before this, and then showed that actually this really was a one. And then 1984, so but this time people were starting to pay attention. So this was really good. So at this point he showed this really interesting, whenever you have a multiply connected Fatu component, so you've got a Fatu component, if it's got a hole in it, then actually it's a wandering domain. So as soon as you know it's got a hole in it, it has to be a wandering. And actually I'll just put the picture up here. So not only is it wandering domain, but actually it has to look in some sense like his original construction did, where he had this sequence of annuli going out to infinity. So for the first few, iterates, it might do anything, it can wander around, but eventually it's going to map, your Fatu component will map to something that surrounds 0. And then it will map to something bigger that surrounds that one, and then it will map something bigger that surrounds that one, and so on.
How does this fit with, how does this fit with the fact that rational functions can have Hermann rings?
So rational functions can't have one domains, kind of, and so if you for a rational function, well, so if we think about a polynomial, you won't get any Julia set outside of a certain. You can't get this behavior that we're getting here in the polynomial case.
No, but for a rational function, you can get a multiply connected Fatou component, which is not a wandering.
Yes, exactly. Yes, sorry. So I should have, yes, okay, this should say if it's an entire function.
Okay.
Sorry, I apologize. Okay, sorry. Yeah, sorry. Everything I'm saying now is for entire function.
Okay.
Yeah. And you can talk about meromorphic, and as Walter had said, yeah, so for meromorphic, it's different again. It's not true that every multiply connected Fatou component, as soon as you've got poles like you have for rational, or in the transcendental case, you can have multiply connected ones that are one-grid domains. They can do different things. But if it's an entire function, yeah, have a all in it, then it will be a one domain and it will have this type. Thank you. And then Phil and I have a paper with Walter Bergweiler where we actually show that not only must you have this structure of infinity, but actually inside each of these, which could be very regular topological annulus, you get a proper round annulus. Where the function behaves really, really nicely. It's behaving like a monic, a monomial, and it will just map that annulus really nicely out onto a bigger annulus, out onto a bigger annulus, and so on. And everything inside your Fatou component sort of gets sucked into this orbit of proper round annuli where the function is behaving like a monomial. So actually, for these multiply connected ones, we can say, just as we can for the periodic Fatou components, we can say exactly what happens. We can tell you that it maps to this sort of orbit of annuli, and we can tell you what's happening to the orbits of points inside them. They're getting sucked into these annuli and going forward like a monomial. And so, in fact, so in some sense, all the points inside here are like these points that Alex constructed, that the fast escaping points, which Phil and I at one point called Eremenko points because they're so nice. They're kind of every point, if you take any small neighborhood around it, that maps eventually covers an annulus, which covers a bigger annulus, and so on. So everything's really, really nice in this setup. You've got a hole in your Fatou component, and you've got multiply connected ones. Okay, so that's multiply connected. So then the question is, what about simply connected? Okay, so we've sort of said that the dynamics in periodic Fatou components are really well understood. There's this classification. Multiply connected is really, really well understood, and you can say exactly what happens. And that you might say, okay, that just leaves simply connected one domains if they exist. What can they be like? But actually, what it turns out is anything can happen. But simply connected one domains that are and this is now a really active area of research. So kind of, it was really interesting having Walter talk before about the escaping there, which was kind of something that we were kind of totally immersed in. And now I'm thinking I must get back to that because we've kind of ended up spending the last kind of few years immersed in wandering domains, kind of, and there's still really big questions about the escaping there. But so these wandering domains, the more you look, you think, okay, actually the periodic ones, they're just these really special examples, kind of, but actually the whole richness of what's going on in the transcendental case is all this huge variety of simply connected wandering domains where anything can happen. So if we just look at points within a simply connected wandering domain, then there's different types of orbits that that particular point can happen. So for a multiply connected one, everything is fast escaping. It goes off to infinity as fast as possible. Most of the early examples, and it's the easiest example to construct it, are examples for simply connected where they are escaping and points go off to infinity. So sort of classic example, this one, this function here. So you've got okay, so you've got a Fatou component here that maps to that one, maps to that one, maps to that one, and so on. And if you didn't have this 2π here, then each of these would just be an attracting base, and everything would be getting sucked into a point in the middle. But when you add on that 2π, because you've got this sort of periodicity, maps to there, so on. So those are kind of sort of nice examples, and nice simple examples in the sense of wandering domains, where you basically have something that's like a sort of periodic Fatou component that might have and you somehow manage to just make it, you have all these multiple copies of it and everything just gets sort of translated across. But you can get much more interesting things than that happening. But that's a kind of nice simple example. So I put an example here. So this is sort of advertising our student Ashton's work. I saw Ashton a minute ago, lost him. Anyway, he has a poster that if you want to look at the kind of wandering cauliflower. So this is Okay, so here you've got there's a Wandering domain. This is a Wandering domain, and it maps across to this one, and it maps across to this one. This is sort of like the kind of classic cauliflower that you get for rational functions, but here his cauliflowers are shrinking and they're kind of going off to the right. So they're sort of, and they're in topology they're getting closer and closer to the well-known classic cauliflower that you get. And that's another example you can have, and loads and loads of research showing that you can think of a domain and you can get it kind of in like a Wandering domain. Okay, so that's escaping Wandering domains. You can also have oscillating ones. These are harder to construct, and the first example of these were constructed by Alex. So this is a paper by Eremenko-Lubitsch in '87, where they sort of used approximation theory. So here you don't know actually exactly what the Fatu components look like, but you can say that you can construct, use this approximation theory to sort of show that you have certain domains that are definitely contained in your Wandering domain. So these ones, they sort of go out, they get bigger, and then you come back in to sort of some neighborhood of 0, and then you sort of come back out again, and then you can come back in, and then you further out again, but you keep on coming in infinitely often. You come back in here. So this is quite hard to control because you infinitely often having to control what's happening kind of in a bounded part of the plane. So this is quite difficult to do. But there are now other techniques, so there are results of sort of Chris Bishop and things, and there's again lots of new examples being constructed of these. And then the last possible example is that the orbit, you might have a Wandering domain where the orbit of each point in there is bounded. And this is a sort of another big open question, so not known if these exist or not. So okay, but there are, so within these two classes there's a whole richness of what can happen. So the sort of initial work that the 5 of us started looking at was, okay, what can we say if we're looking inside of Wandering domain? So for these other components we can give a really precise description of the dynamics. I mean, we could see straight away that just by looking at examples, it's not going to be as simple as that. You can already see that there are examples that look like wandering, attracting, or wandering, so on. So it's not going to be every simply connected Wandering domain inside it's like this. But what can you say? Kind of, can you start to get a handle on it? Okay, so we have sort of various results on that, and then I say that sort of led us to kind of generalize out from there. So, okay, so we have a sort of paper when the aim was to sort of classify simply connected Wandering domains. Okay, so the original aim is to classify in the same way that you might periodic, but it's more complicated than that. So we actually ended up with sort of 2 3-way classification. So we sort of looked at what you could say about the dynamics in from 2 different perspectives, kind of, and for each of these 2 different perspectives we get 3 different possibilities. Okay, so the first possibility is thinking about if you have your orbit of Wandering domains, and then you're looking at points inside that, what happens to the orbit of points relative to their distance from the boundary? So like if for a periodic attracting component, for example, everything gets sucked into the middle, kind of the parabolic, everything is going to the boundary. So what happens if you have an orbit of these simply connected Wandering domains? Are points coming into the middle? Are they going to the boundary? Are points, just because one point is doing that, what's happened to other points? So, okay, so basically you get the 3 possibilities that you might think straight away. So first, everything stays away from the boundary. Second one, bungee. Okay, so the letters are chosen to match A, B, C, kind of. But so bungee means points go arbitrarily close to the boundary. They sort of get closer and closer to the boundary and come back into the middle. And sort of converges to the boundary. So obviously for one particular point, that's the only 3 possibilities you could have. But the kind of what we're showing is that if one point, the orbit of that always stays away from the boundary, then all the points kind of will stay away from the boundary. And if one point goes, arbitrarily close to the boundary, keeps them, then all the points in the side. So the key thing really is that all the points are behaving together. They're kind of moving together. And also the interesting thing is that we give a technique that means you can show that all 3 of those types of possibilities can occur. So all the examples before that were either in the first one or the third one, but this middle one where you sort of put the boundary, and that was known, that was not, there were no examples like that we constructed once.
So when you say stays away or converges, you mean the Euclidean distance is bounded from below?
Yes, yes, yeah, and there are different ways you could, we sort of show that there are different ways you could describe the boundary, because so one of the things you have to wrestle with is that they could be, like in Ashton's example, they could be shrinking. So, I mean, the default is we just take the Euclidean distance kind of, but you could somehow scale, there you are, Ashton, sorry. But you could scale by the diameter of something, but of course your one domain could be very distorted. So what does that mean? And so, yeah, but the sort of top level definition is just Euclidean distance. Okay, so that's the first classification, and then the second classification is respect to hyperbolic distances. So here, if you have a pair of points, then you're looking at, as you follow the orbit of that pair of points, what's happening to the hyperbolic distance between them. Now, if you have a domain that maps to another domain, the hyperbolic distance of a pair of points must decrease or stay the same. That's all you're allowed to do. So the thing is, what happens if you look at all the points kind of together? And again, you have the same behavior for everywhere, kind of. So if you have one pair of points with distinct orbits who get closer and closer and closer together, and the hyperbolic tends to 0, then that's going to happen for everything in your one domain. You get the same, all the points behave each other. So this is the first possibility, that it's contracting. So the hyperbolic distance is decreasing to 0 for every pair of points that have distinct orbits. That one we call semi-contracting. So it's decreasing. You've got many n for which, when you look at the hyperbolic distance at the next stage, it's strictly less than the distance here, but it never actually, it's not tending to 0, it's tending to some finite limit, but it does keep on decreasing ever so often, kind of. And then you've got the final case when it's eventually isometric, so the way that it settles down to the kind of the hyperbolic distance stays the same from some stage on. So again, the sort of examples that were known, kind of this sort of recently large family of examples, we knew there were examples of the first one, the third one, but not the second one, kind of. But we could construct examples of all 3. And if you put these 2 3-way classifications together, you get 9. And we have examples for all of those. And so there are only, when you put them all together, there are only 3 types that were previously, but now you have these 9 different ways that you can 9 different types simply connected bonding domains. So even if you look at this kind of sort of quite top level in the sense of kind of what's happening in terms of going to the boundary or the distance between pairs of points, you still get 9 possibilities. So that the periodic Fatu components, is only kind of like 5 different types of periodic Fatu components. All of them so far, in a sense, is quite a top level kind of what's going on, and you've still got 9, and then you could, within that, the whole richness of stuff that you could look at. But still, this helps to kind of, you know, classify them to some extent.
Is there one example where all 9 things happen?
No, so you can only be one. So each example, you have to be one of these 3 types and one of the other 3 types.
No,
but I mean for
think
different
you meant one
components.
function where you have
function with
9.
all-
I see what you mean.
You can have different components.
Yeah. Sorry, I see what you mean. 9 orbits of 9 different types of. Well, we haven't.
Well, but then
We could do that. Yeah.
approximation theory, right?
Yeah. So it's approximation theory that we use to kind of do sort of with the kind of new technique. Of,
Yeah, so I'm just pointing out you don't need 9 examples. You
yeah.
can-
I didn't. Yeah, I didn't say 9 examples. But I agree. Yeah. No, you're right. We could put them all on the same picture. Yeah. Okay. So what I want to do is just kind of not sketch the proof, but just kind of show how we sort of think about these, because that leads on to the next part of the. Okay. So how do we do this? Which is why I want to do the board. It's easier to draw these things. Okay. So you've got an orbit of 1 ring domain. So we've got our U here, and we just take any point Z naught in our domain, and then we map that to U1. I'm drawing these as kind of bounded, kind of fairly simple things. They could, of course, be much horrible, but you know, but let's just, okay. I've got F of Z naught here. Okay. So I keep on mapping by this is quite a nice board actually. Right. That's not a piece of chalk, man. Okay, so then what we do is basically just transfer everything to the unit disk, where everything's much simpler. So we're just going to take the Riemann mapping here. You get unit disk. And each stage I'm going to map the orbit of this point here, I'm going to map to 0. Okay, so I've got 0. Unit disk here. These are all supposed to be copies of the unit disk. I'm sorry, they don't look very circular, but this is 0. And so on. Yeah, and each time I'm using the Riemann mapping to get. So what I end up with at this point, I've got a self map of the unit disk to itself. It's actually an inner function, which I'll put the formal definition of that in a minute. And I've got here, we start off with we have the same function f going each stage here. When we go down to the unit disk, we've got a different function at each stage. So we've got G1 here, got G2 here, Gn, and so on. So we've now got a sort of composition of different self maps of the unit disk, and each of which fixes 0. And we're going to look at the dynamics on that. And that's something that's kind of the sort of results that we can apply. So that's.
Is there some kind of relation between the GNs caused by the fact that you have the same F?
So that's what's interesting. You can get any function Gn on the bottom. So actually, we can construct one sort of almost going backwards. You could our original construction of where we get them. Like you can specify any functions you like here, and we can get a one-line domain that basically is behaving like that thing. So even though you start off with the same f here, because actually it says f here, but so it's the same global function, but the map from here, at each stage, it's kind of behaving really differently. So in some ways it's helpful, I think, to do this picture just because it really emphasizes that this f is slightly misleading here. It looks like you think like you're taking the same function.
So a totally different part of the domain.
It's a different part of the domain, exactly. So I think this picture is actually much more helpful because it's saying actually each of these is a completely different map, really, and we can there's nothing that stops us kind of putting whatever we like down here. And that's why there's such a richness of behavior, because we can kind of just
Where periodic you would have gotten a cycle, and at some point use the same functions over and over again.
Yes, exactly. Yeah. So the periodic factor components, you could do exactly this argument here, but you would stop here, and so you only so it's much simpler So this is why these one domains are so interesting, that you can get a different function every stage.
But is it really that if I give you a sequence Gn, then you can sort of construct the F? Or...
Wow. Okay, so if you give a sequence Gn, we could kind of approximately
Okay.
But kind of morally, you can there's certainly a huge
There's some authors here who think they can do better than that.
Okay, right. I should let you say something.
If it's a finite Blaschke product, then you can get exactly.
Yeah.
Okay. This is the paper that.
It's not yet on the archive.
Yeah, it's not on the archive yet. Yeah. So watch this space. But the morally you can do a huge number of things here. Okay, so what have I put here? Hopefully this summarizes something. Okay, so this is the Riemann mapping, which we're mapping down there. And then we look at these inner functions that we've got on the bottom. Okay, and then what happens here, we kind of look at results that are there. So there's a sort of nice result from Alan Bearden and Keith Kahn. And what happens at this point is basically the dynamics here, when you, in terms of the kind of contraction and what's happening about distances between points, and what's happening in terms of, is G, are these 0 or not? It depends on the derivative 0 of these functions. So okay, so what you're going to get here is that when you follow this orbit here, all these points here get sort of closer and closer into zero as you go along, precisely if this sum is divergent. So this is kind of, so you know, the smaller the derivative at the origin is, the sort of more contracting is, and the more things get set into zero, which is sort of makes sense morally. Okay, so that's kind of the end of the first part of the talk, and that was, you know, so that's where we started. It was really say, okay, we know everything about periodic factor components multiplicated. What can we say about simply connected? And you get this classification, and you get lots of examples. But now we've sort of moved into this different world in a sense. So we've kind of moved into these sort of compositions of inner functions. So we've got self-maps to the unit disk, and these didn't need to have come from wandering domains, kind of. So the sort of second part of the talk I want to look at is, okay, let's just, for now, we can forget that these came from wandering domains, and this is a kind of more general question in a sense. What can you've now got this non-autonomous system with these different maps at each stage, mapping the unit disk into itself. What can you say about the dynamics there? And can you sort of build on this and get a more general theory? Okay, so right, so this is part 2. Okay, so it's dynamics of inner functions. Now we've moved into this setting here, kind of, but keeping in our heads where we came from, that we want to know about wandering domains. Okay, so sort of formal definition, kind of, it's a holomorphic self-map of the unit disk, and in particular, if you sort of almost everywhere, it's kind of, you can sort of you've got a nice extension to the boundary by a radial limit. So almost every point on the boundary here, you can sort of extend it and map to the boundary here. And I'm just going to use the same, you know, this might have only been defined in here, but I'm going to use the extension to the boundary. I use the same notation. But we just have to remember it may not be defined everywhere on the map. Okay, so, but you could have more, you know, nicer. You could have really polymorphic on the disk to itself. Okay, and for when you come from wandering domains, obviously the function you're going to get nice domain. Okay, so right. So examples of inner functions, you can, so sort of classic things are Blaschke products. So these are sort of products of Möbius maps of the disk to itself. So you could have finite degree, you can have infinite degree, and you can have ones that look completely different to that. So this function here is a inner function, so that's not made up of a Blaschke products. So there's lots and lots and lots of examples of inner functions. Okay, it's something that, you know, people study in their own right. And so what we want to, so there's lots of sort of classical results on iterating inner functions. So you take one, you have an inner function matched to the unit disk itself, and you can, exactly as we started off talking about, you know, Fatu-Julia theory, kind of, and the whole plane, looking at iterates of your disk to itself. What results do you get? And what we're interested in here, because we've ended up, the system here didn't give us the same map each time, kind of, you would have got if you know, if you, well, we've reduced that ability to it, you want to know that having different maps each time. So what happens if you just do these compositions of different maps? So you get this non-autonomous dynamics. So the starting point really is to look at what the classical results are for just repeatedly iterating one inner function, looking at those and say, okay, now what happens if instead of iterating one inner function, we look at picking compositions of different inner functions at each stage. Yeah, okay, so I've got FNs instead of GNs, apologies for that. I'll probably move back to these FNs here. And in some cases, these FNs that you get here, you could have just defined a sequence here from this one to here without necessarily going through this composition. But some results you really do need to have gone through the composition, others will kind of hold more general. But we're mainly sort of driven by composing maps and seeing what happens. So sort of classic kind of, we'll start off with the iterates is the Donald-Wolf theorem. So if you, this says that if you have a function, so up to this itself, as long as there's not a rotation about a point, then the Donjon-Wolf point, and everything, if you keep on iterating your function, everything inside your disk is going to converge to this Donjon-Wolf point. So the Donjon-Wolf point might be inside the disk, or it might be on the boundary of the disk, but you've got one point, and all the iterates of all your points inside are converging to that Donjon-Wolf point. So that's really nice. What happens if you take compositions of different functions at each stage? Do you still, you're not going to get exactly this, you're not going to get a sort of fixed point here, because you could, these maps are, you can kind of just introduce a sort of slight rotation at each stage or something if you wanted, but does everything all converge together is the question. Okay, so this is the first paper, I think this is paper. So, okay, for this result, actually, you don't have to have compositions. You just have a sequence of holomorphic maps of the self-disk, of the disk. And if you've got one point in your disk, which is going to the boundary of the disk, then all the other points in the disk will also go to the boundary, but not only will they go to the boundary, they'll sort of go with that point in the middle. So all the sort of points are moving forwards together. So as long as you know one point going to the, it could be kind of getting close to here and then going here and then going out there, and then everything in the disk will sort of converging together, kind of same type of behavior. So everything the same limiting behavior. I say that sort of, you have to bear in mind that you're going to a different stage at each time. So there's not a sort of fixed point on the boundary that you're tending to, but everything's going together. Okay, so then the sort of question which is sort of naturally out of this is that, okay, we know what's, if we've got everything on the inside of the disk, it's all getting sort of going together towards the boundary in the same way, what's happening on the boundary? So if everything inside is kind of, sort of going to, say, getting close to here and then here and then here and then here, are all the points on the boundary possibly, are they all kind of coming towards the same kind of limit of the interior points, or perhaps they're doing completely different things, or what's happening? So again, the sort of starting point is, okay, well, what do we know about if you've got an iterate in terms of how the points on the boundary, the iterates of those behave, and then what can we think about generalizing? So if you just iterate in functions, it's a really, really nice dichotomy. So you've got an inner function, you're just iterating it, and you've got the points in the middle are all going to the, so in this case, the Donjon point we're saying is going to on the boundary. Then so the sort of a mixture of results, you can go back to so the sorts of Aronson and Doering and Manier, and there's two distinct cases that can happen, and that what makes the difference is depending on how quickly your point in the middle is going towards the boundary. So if you take 0, we could take any point because all the points inside have the same limiting behavior. If this sum is finite, so that means that if your point 0, if when you iterate it, it goes to the boundary quickly enough that when you add up all these, this is distance from this point to the boundary here, 1 minus that. If you add up those distances to the boundary, and that's finite, then actually all the boundary points have the same limiting behavior. So all the boundary points go to the Donjon-Wolf point. Okay, so everything inside is converging to this Donjon-Wolf point, and because it's going really quickly to that Donjon-Wolf point, it's sort of something that's sucking in everything from on the boundary is also doing exactly the same. On the other hand, if it goes slowly, so that if it's going to the boundary slowly, that this sum is divergent, then you get completely the opposite. So if it goes fast, everything goes to this Donjon-Wolf point. If it goes the boundary slowly, then the iterates in the boundary are actually dead. So it's, as you really have got these two completely opposite behaviors. Fast convergence to the boundary means that everything on the boundary gets sucked into the Donjon-Wolf point. Slow convergence to the boundary means that the orbits on the boundary are just going everywhere, and they're kind of, it's just So really interesting dichotomy there. So that obviously the question is, okay, well, what happens instead of looking at iterates of points? We look at our situation here where we're taking a different map each time. So it's, let's suppose we know that all the points inside are going towards the boundary. And we know that if that happens, we know they all go together. If the interior points go to the boundary quickly, do we get all the boundary points sort of having the same limited behavior as well? And if they go slowly, do the boundary points just behavior on the boundary? That's the question. Look at. Hopefully that's, yeah, okay, I'll come back to that later. Okay, so the first part is actually much easier than the second part. So the first part is if everything on the inside goes to the boundary quickly, then we can show that everything, the boundary, almost all points on the boundary have the same limiting behavior as well. So this goes through quite nicely. And actually, we don't even need the composition. We can do it with general holomorphic functions, and we can even get a result where we don't look at maps of the disk. We look at different simply connected domains there, but then you do need to take into account the geometry of the domain, and the formula changes a bit. But essentially, if you've got everything everything on in the inside going together to the boundary quickly, it will suck all the boundary points will have the same limiting behavior.
So I'm slightly confused all of a sudden. So in your example there, from
Yeah.
which you were starting, you were always mapping the origin to the origin with the G's, right?
Right.
Doesn't that mean Fn of 0 is always 0?
Yeah. Okay. So yes, I agree. So I've now I should kind of I've now shifted to a case where where I'm allowing I'm actually going to come back to this. I'll tell you what I'm going to do.
In this case, you will always have this condition. Is that right or no? I mean, if you take your
No, in this case you'll have the opposite. In this, if you've got 0, 6.
the sum of one is infinity.
Yeah.
You always have the opposite. Right?
Yeah, you always have the opposite. But
Okay.
but yeah.
Yeah.
So,
all right.
and actually, yeah, but it is so interestingly enough, what we're going to do, we're interested in kind of letting these go to the boundary. We're going to prove things actually interesting. They're coming back to the situation and looking at a proof in that situation. So I think
So formally it can be applied to also to Fuchsian groups of convergent type, right? If you have a Fuchsian group of convergent that satisfies Blaschke condition, then everything follows, everything on the boundary follows the orbit, the limiting set.
as long as they're holomorphic maps that you're looking at, then yeah. And I say in this case, they don't need to be compositions. Okay. Right. Okay, so what about so we can generalize here, but what happens if what we want to know is, okay, now suppose we've got interior points going to the boundary slowly, so that some is divergent. Do we get sort of something about dense orbits on the boundary, or what do we get there? So that's what you'd like. The first thing is you'd like to get that, but actually we don't get that. So the first thing is that we have a counterexample to part B. So we've got something where we've got the examples where you have these composition linear functions. The interior points are going to the boundary, but they're going to the boundary slowly, so this sum is divergent. And yet still everything is going, all the boundary points are following the same sort of limiting behavior as the interior points. So we've got the same, we're in this case where even we have this conclusion, even though we have this divergent. So then you start to get, okay, well, what can we do? Can we put some extra condition on there? Maybe, and if you go back to one thing is going back to the iterate case, if you have that this sum is divergent, and you have, if this is f to the n in here, and this sum is divergent, then what you can show is actually you can show that your iterates are contracting, so that the points, which is the hyperbolic distance between your pair of points, is tending to 0. Whereas for this general case here, when we allow different compositions, this sum being divergent doesn't mean you can have that when you haven't got contracting. So suppose you add on that contracting condition, which has to happen in the original dichotomy. Does that help? So that was our original conjecture. do this thing. But actually, it turns out that even that is not enough, kind of, and actually something much more interesting happened. So I should give the. So, yeah, okay. So we had this question: if you have contracting, so the hyperbolic distance between all your points is tending to 0, and you're going to the boundary slowly, do you get sort of dense orbits on the boundary? Right. So what it turns out that it's sort of what happens is related to this so I've got the hyperbolic distortion along your orbit. So this is basically the derivative with respect to the hyperbolic metric as you go along your orbit. So you're following your orbit of your point 0 in here. And what's happening is very dependent on what the derivative is here. So there's sort of two interactions going on. So it's not as simple as it just have to be contracting. It's kind of, so what you get is you get this result here. So what we get is what we originally wanted to get a sort of generalization of the iterate case, which we wouldn't have this term here. We would just have that the sum of this distance from the boundary. We look at this orbit of 0 to the boundary. If this sum is divergent, then we'd like all the orbits in the boundary to be dense. But actually what turns out is that you have to put this factor 1 minus lambda. So you've sort of got this interplay between the derivative along your orbit and how fast it's going to the boundary. So actually, I think it's really, I think it's nicer than we originally think because it's more interesting, kind of, and it's especially interesting because it's sharp. So it's not just that we can't, sometimes you prove result and you go, well, the best we can do is this kind of. And it's really annoying because we'd really like to get rid of that factor there, but actually you can't get rid of that factor. We have examples which show that that's the best you can do, and you really do need that factor.
But you don't have the full dichotomy, so that if that converges, you don't all go to one point.
We do have that. Yes, sorry, I had that on. I think I had that on an earlier slide. So yeah. So actually, for the
Oh, that was on the
yeah. So actually, I've got this on a later slide, I think. But if you have that sum without that factor, if that's convergent, then everything goes to the, everything has the same limiting behavior, goes all to the boundary together. If you have it with this sum, then you get dense. With this factor, you get dense orbits, and then that leaves you a sort of grey area in between. And actually, there you can get both different conclusions can happen depending. You can construct examples, and it depends on how you. Yeah. So, yeah. Okay. Right. So, yeah, contracting is if you have this sum is divergent, and this condition implies that this sum is divergent, but it's like it's not, and it implies that sum's divergent and implies that sum's divergent. So both of these must be divergent, but it's that interaction there. Okay. Yeah. So they have to be sufficiently contracting in relation to the how fast you're going to the boundary. So there's this interaction. Oh, okay. So that's the result. Yeah, we've got examples which show it's sharp. So, okay, so the proof of this is through shrinking targets, which I really, really like. So, okay, I'm going to replace my wandering domains here with. Which I think relates to, like, maybe it was somebody pointed out earlier that I'd switched from points going to 0 to right. So my original setup here is my self maps to the unit disk, but I'm starting with 0 here, and then 0 is going towards the boundary. Okay, so I've got f of 0 here, got f1 of 0. So this is f1 of 0 here. I map by my inner function here. I keep on mapping by my sequence of inner functions. At this point, now I've got quite close to the boundary here. But in a similar way to how we think about the wandering domains, I'm going to map sort of centralize this because it's easier to work with things when we fix 0. So we're taking sort of Möbius maps here with sending this orbit of 0, we're getting it 0, and then thinking about a. So if what we want to show dense orbits. So we've got this, and our assumption is that this is going boundary. Yeah, it's boundary slowly. So to show that we've got dense orbits on the boundary, what does that mean? It means that if we take any arc on the boundary here, take the same arc each stage. This is, fixed interval I. I want to show that almost all points on the boundary land in this interval I infinitely often. So that's what the dense orbits means, that we kind of land in this interval infinitely often. The question is, okay, let's get it to this situation here where we can work with things more easily. What does that mean? And we do that, these intervals I here, you're going to get an interval, a different interval here. So this is I1. The interesting thing is that the size, when you do this sort of normalization here, the sort of size of this arc here, this sort of target that you want to hit, it shrinks, and the size of this target here is basically proportional to this distance to the boundary here. So if your distance to the boundary is 10 to 0, you've produced a sort of sequence of arcs here that you want to hit in your centralized sort of ones here, and we call it, makes sense to call it a shrinking target. We've got shrinking targets of arcs. They're not nested kind of, but but you've got a sequence of arcs from the boundary and they're getting smaller at each stage. And the question is, how many these arcs here? So I think that's what I've just put on this slide here. It's basically sort of get through it, but it's basically saying let's go to this normalized. So up here we've got 0 fixed, and what we want to do is we want to hit this shrinking target of arcs IN infinitely often. We're going to prove that. Okay, so yeah, so I basically just written here exactly what we're doing. Yeah. So we want to show that the set of points which hit this shrinking target infinitely often has full measure. Okay. So what do we get? So this is what we prove. So now it's sort of we go through various sort of formulations of this problem, but we've now kind of start off with one and we end up kind of looking at these functions where we've got 0 fixed here and we've got shrinking targets there, and it's just turned completely into a question about, if I've got a shrinking target of arcs, when do points on the boundary hit it and when don't? Okay, so what we get is that if you we have this condition, which is what we so that the size of the arcs times the derivative at the origin, if that's divergent, then almost all points are going to hit that shrinking target infinitely often. And this comes back to the question which you asked. If this sum is convergent, so without we don't need that factor in there, then almost nothing will hit your shrinking target. So your shrinking target is now so small that almost nothing can hit it. And I say, if we're the intermediate stage where this sum is divergent, but this sum is convergent, then we can get examples to show that you can have either possibility. And there it really depends on how these arcs IN sort of line up with each other. When you're sort of looking at pre-images of them, we can set examples that going on, which I'm going slightly off my size here, but essentially what's going on is you pull back each of these arcs here, and you want to know how many points lie in infinitely many pre-images of these if you pull it all back to the beginning here. And because it's the size of these pre-images in here is exactly the size, say, as the size of the set you started off. So the pre-image of I1 in here is the same as the size of I1. So if the sum of your INs is convergent, you're pulling back and you've got a sum of arcs who, a finite length, and the set of points that can lie in infinitely many of those little Borel-Cantelli thing, and it's just almost no points lying there. If the sum of them is divergent when you pull back, then it depends on whether they all lie on top of whether the pre-images somehow all stack up together and lie on top of each other, in which case you're going to get a lot of points that aren't in those pre-images. Or if they all spread out enough around here, then you're going to get that almost all points must be an infinite many of the pre-images. So it just depends on how these pre-images stack up when you pull them back. Let's see what I actually put on my slides. Okay. So yeah, so this is okay. So the way we do it is we want to do it in this general case where we've got different rates of contraction going on in each case, but that you can prove it if you know that each of the functions that you're applying has the same, the derivative has a uniform upper bound here as you get each stage. It doesn't matter what it is, but you have to have some bound. So we can prove it, and in that case, we can prove that if the rate of contraction is uniform, then actually, as long as some of your shrinking targets is infinite, then you're going to hit almost all points will hit infinitely many of your arcs. Okay, and I think this is where I just kind of found what I did here. So we want the points to lie in infinitely many of the images of these sets back here. And I say if this sum is divergent, then almost no points will lie in them. If it's divergent here, then we use two things. So if it's convergent, use Borel can tell you 1. If it's divergent, use Borel can tell you 2. Plus sort of mixing result of Pomerenke here, which we put in here to show that you must get this. Your pre-images are going to be sort of uniform, spread out enough that you can get that almost all points lie in infinitely many of them. Okay. And then the sort of final thing which you do is this is kind of when you've got this uniform rate of contraction for your functions, but we wanted to have something dependent on the rate of, we wanted to be able to have arbitrary rates of contraction here. So the last bit to do is, okay, you have this sort of the simple case when you've got uniform contraction. If you have different rates of contraction, then what we do is basically group together. We sort of do this blocking thing. So we will go along in the stages until when you compose those maps, that gives you a certain rate of contraction, and then we'll do another block until we get that rate of contraction, and then we'll do another block that rate of contraction, and then apply the result for uniform contraction. And at that point, it kind of that's the interplay between what the size of your targets are and what your rate of contraction is comes into play, and that's where it feeds in. Okay. Okay, and then final slide going, okay, but what about wandering domains? So we started with wandering domains kind of going, that was how we ended up going into these this sort of non-autonomous dynamics of inner functions. But what can you say about wandering domains? So some of the things I've said already that you can do, it's kind of it's non-trivial when you look at the boundary and what's going on, because the geometry of your wandering domains can be so different, kind of. I mean, if the wandering domains all happen to be like circles, then you would be able to transfer everything back exactly like we just talked about for the inner functions. But it's going to be more interesting than that. So this is kind of just a sort of first. This is the end slide, but it's also the first slide of kind of what will be the next talk in what you might do. So what did I put here? Okay. Right, so let's just very quickly put just okay, imagine these are now wandering domains. So they have distorted shapes, and they could be here. Then basically what you're going to try and do is transfer back your results about shrinking targets that you have in this system using the sort of Riemann mappings that we had before. You can sort of say something as a starting point that if you have a sort of angle here, and then that kind of goes to say something like this, that if you kind of hit a sequence of arcs here, you're going to get points that land in kind of sequences here. But what this actually means when you start putting it back, given that your whole geometry could be very, very irregular, is going to be much more complex. So I won't go into this kind of figures, but it's just to sort of and especially given the time, I will just sort of say that you could do something along those lines, and I'll skip past that. And I finish there with saying happy birthday to Alex, and This is the construction. This is the sort of picture from his paper where the paper where they construct these oscillating polynomials. And my laptop, for some reason, it coloured it in a very sort of blotchy kind of way. Okay, thank you.